All right, we are about to dive into one of the biggest, most important unsolved mysteries, not just in computer science, but maybe in all of science. It's a question that has a $1 million prize attached to it, and one that could literally change the world as we know it. So, to get our heads around this, let's start with something really simple: a puzzle. It's based on an idea you already know, you already feel in your gut, but it's right at the heart of this gigantic problem. Just think about a jigsaw puzzle. Finding the solution, taking all those hundreds, maybe thousands of pieces from a jumbled mess and putting them together. That can take hours or days or even weeks. It's genuinely hard work. But what about checking the solution? If I hand you a finished puzzle, you can tell if it's correct pretty much instantly. You just look at it. That gap, that massive difference between the effort to find the answer and the effort to check it, is what this is all about. And this right here is the core mystery. Is this huge gap between finding an answer and checking an answer a fundamental feature of our universe? Or is it just that we haven't been smart enough yet to figure out the easy way to solve the puzzle from the start? Okay, now let's put some official names on these ideas. In the world of computer science, problems get sorted into different groups based on how hard they are. The two main characters in our story today are called P and NP. So first up, we have P. The P stands for polynomial time, which is really just a fancy way of saying these are the easy problems for a computer. Think about sorting a playlist or searching for a contact in your phone. Yeah, if the list gets way bigger, it takes more time, but the work grows at a totally manageable, predictable rate. We have really good, efficient ways to solve these. And then we have NP. This group includes all the problems where if someone just gives you a potential solution, you can check if it's right really, really fast. Our jigsaw puzzle? That's an NP. Same with the famous traveling salesman problem. If someone shows you a route that visits 100 different cities, it's super easy to add up the distance and see if it works. But actually finding the absolute shortest possible route, oh man, that is brutally, ridiculously hard. Okay, so we've got P, the problems that are easy to solve, and we've got NP, the problems that are easy to check. Now we can finally ask the big one, the question that has stumped the brightest minds on the planet for decades. Does P equal NP? To put it simply, this is asking if a solution to a problem can be checked quickly, does that automatically mean that the problem can also be solved quickly? Are finding and checking actually the same thing deep down and we just haven't found the clever trick to it yet? Now, this question is so profound, so absolutely fundamental, that the Clay Mathematics Institute has named it one of its 7 Millennium Prize Problems. And yeah, that means whoever can provide a real proof for the answer gets a cool $1 million prize. Now, let's just imagine for a second what would happen if the answer was yes, because this is where things get really wild. If P does equal NP, it wouldn't just be some academic victory. It would completely shatter the world as we know it. For starters, all modern cryptography would just collapse. Your bank accounts, your private messages, all the government secrets, they're all protected by encryption that's built on one simple idea: that some problems are hard to solve but easy to check. If P equals NP, that hardness just evaporates. Any encrypted message could be broken in a snap. But on the flip side, we'd suddenly live in a world of perfect efficiency. We could solve some of the most complex puzzles imaginable. We could find the single most efficient airline schedule to get rid of delays forever, or design flawless computer circuits, or even figure out exactly how proteins fold to cure diseases, all by finding the perfect, optimal solution instantly. And maybe the most mind-bending part of all, mathematics itself would change forever. See, checking if a mathematical proof is correct is a pretty straightforward task. It's an NP problem. If P equals NP, then finding the proof would suddenly become just as easy. We could essentially automate creativity. Computers could start discovering new, profound mathematical truths all on their own. So how do you even begin to solve this? How could anyone possibly prove something that applies to all of these different problems? Well, as it turns out, researchers discovered a fascinating clue, a special kind of problem that holds the key to the entire mystery. They're called NP-complete problems. You can think of them as the hardest of the hard problems inside NP. That traveling salesman problem, complex scheduling, protein folding, hundreds of these incredibly important practical problems all belong to this one exclusive club. And they all share a remarkable, almost magical property. They're all connected. It's like a giant chain of dominoes. If you could find a fast, efficient solution for just one single NP-complete problem, it doesn't matter which one, that solution would act like a master key. You could then use that one key to unlock an efficient solution for every other problem in NP. You crack one, you crack them all. And in one single move, you would prove that P equals NP. But here's the thing. So far, no one has found that master key. And after decades of the smartest people in the world trying and failing to find it, we've basically had to learn to live in a world where we assume it just doesn't exist. The overwhelming consensus, if you ask the experts, is that P does not equal NP. They believe that some problems, like our jigsaw puzzle, really are fundamentally harder to solve than they are to check. But, and this is the whole point, it's still just a belief. There is no proof. And because we all operate on this unproven assumption, we've built our entire technological world around it. We've basically accepted that we can't always find the perfect answer. So instead, we've developed all these clever ways to find answers that are good enough. You see this every day. When your GPS calculates a route, it's not actually finding the single mathematically shortest path. That would take way too long. It's using a smart shortcut, what's called an approximation algorithm, to find a very good route very quickly. The same thing is true for airline schedules or package delivery routes. Our entire world runs on good enough because we assume perfect is just too hard to find. And that leaves us right here with this final profound question. Is the universe wired in a way that makes some things genuinely, fundamentally hard? Or is that gap between finding and checking just a failure of our own imagination, a puzzle that's just waiting for some future genius to find the simple, elegant solution that's been hiding in plain sight all along? We just don't know.